computer networking technologies, because it is trying to basically tell you that TCP/IP sucks and sucks hard, and we have something that is kind of the better alternative for a lot of problems of current internet.
So, okay, thank you, Vladimir, for introduction, and I will start right away. Then, my name is Marcel Marek, and I will present to you our creation RINASim that we've been developing here for past 2.5 years. So, first, the agenda. It will be really quick. I will mention something about Project Pristine that our simulator is developed within. Then I will mention something about RINASim. We'll go a little bit into detail about the structure of the main components and some dissemination and references. So, Project Pristine. Project Pristine is something called programmability in RINA for European supremacy of virtualized networks. It's really, really long, but it's project from European Union. There are about 15 partners around Europe, as you can see on the map. Hopefully you can see on the map. The total cost of the project is mentioned here, and it is running since January 2014 to June 2016, and it was extended to October. So yeah, we're a little overdue, but we have some things that we want to push, so we extended the project. As you can see, there are partners all over Europe. For example, there's the University of Oslo, there are Atos from Spain, and some German partners, some from Italy. So yeah, we are working with a lot of guys. And straight to RINASim. I hope that most of you heard Vladimir's presentation from Zurich, when he was explaining what the RINA really is, because otherwise it will be not so interesting for you, this presentation, because I will skip the nature of RINA, but let's just say that it is a recursive inter-process network architecture. It is, the concept is that there is no 7 layers like in ISO OSI, but there is one generic layer, then you can repeat as many times as you would like. That's the recursion in it. So, and so RINA Simulator is fully fledged. RINASim is fully fledged RINA Simulator. It is built from scratch, so there is no usage of some, let's say, INET codes or other stuff. It's a clear framework built from scratch, and yeah, you can find it on this URL. It's not so convenient, but it's not as long, so hopefully you will be able to find it. And some slug statistic. If you remember, Vladimir showed you that our ANSA INET has about 25,000 lines of code, and just to say that my presentation is better because our RINASim has 26,000 lines of code without any comments and stuff like that, and that is just pure C++. When you include the net file and just INI and XML files, it got together almost 100,000. So yeah, it has to be better because it has a lot of lines of code, Yeah. Like I mentioned, there's a lot of partners on the project, but the partners that are actually actively developing the RINASim are here. Here at FitBeauty, we developed the core, the mechanism, as it is mentioned in RINA, and the other partners mentioned here usually develop the policies that they want to use, for example, congestion control, or for routing, or for forwarding table generator. So one partner decides that they want to deal with congestion. They don't have to implement the whole stack, or they don't need to change anything that are not interested in, but they only implement certain policy that handles congestion in the node, and that's the, let's say, whole work that they have to do. Of course, it's not as simple as I said, but it's they can concentrate on really certain topics that they are interested in, and then they don't have to implement the stuff that they are not interested in. Okay, and go a little bit into the detail. This is how looks our three types of hosts. So you either have the end node, the host, then you have some interior router, and then you have the border router. The difference between border router and interior router, you can see that there's this IPC is colored with different color, because this IPC belongs to a different layer called div in RINA, but let's use term layer. So this one belongs to layer below, and therefore it can communicate with IPCs in the another layer. And okay, here you can see there are two IPCs on top of each other, but those IPCs are the same. They have the same structure. You don't have to implement one type of IPC here and other IPC here. You implement one IPC and then you just replicate it as many times in the node as you would like, and you just interconnect them.
This is this generic layer, you know? Instead of networking layer, datalink layer, transport layer, we have only one layer with programmable functionality, and you can achieve different kinds of use cases using this one layer that you can recursively stack.
Yeah, if you, for example, would like to kind of hide your network as an ISP, you just create your div that is below, and your IPC communicate with the customer, and all your network is hidden. It's transparent for the customer, and the data just goes through a black box and appear at the other end. And here is how the model of IPC actually looks like. It's right here. So there are few components main. The EFCP, that is the transport protocol. It's called error and flow control protocol. It handles both flow control or both error control. If you want a reliable connection, you can turn it on. If you don't need a reliable connection, those policies are just empty, and no acknowledgement or negative acknowledgement are not sent. It just depends on the configuration.
Basically, it mimics the behavior of TCP and UDP. You know? Instead of having multiple different transfer protocols, we have only one with different policies that you can turn on and off to achieve either reliable connection or unreliable, either connection-oriented or connectionless.
Yeah, you don't have just UDP that has no flow control, no reliability, and then a TCP with both, but you can have anything you can imagine in the middle, just because you can turn on. Yeah.
For instance, or this kind of combination that are not present.
I will show it to you in, well, not call it a demo because all demos fail, but I will show it later to you. So here it is. The EFCP is connected to some module called delimiting that does the fragmentation and some reassembly on the other side. And here you can see the inside of the data transfer. Here it is only in mode like UDP, so there is only DTP. There is some component called DTCP, that is data transfer control protocol, and it maintains the flow control, reliability, and stuff like that. Yeah, and what's the other flow allocator that handles creation of a new flow. So when an application entity wants to communicate with some other part, this flow allocator create instance called flow allocator instance, and it handles too much details. Okay. Okay, then there it is. It is all. And
one more return next. Sorry for interrupting your presentation. What is interesting about this, let's say, RINA architecture is that basically we needed to create everything that is currently present in TCP IP from scratch, which includes routing, which includes transfer protocols just like TCP, UDP, which includes delimiting and fragmentation if something is above the NTU of the link. So a lot of these things are happening over there. Like we needed to create unicast communication, multicast communication, something that is called in RINA is whatever cast communication. Doesn't matter what number of recipients there are. It is basically about just name. If there is a name, if there is kind of address that belongs to multiple nodes, it will be a multicast. If it is address, it belongs only to one node, it will be automatically unicast. So different kind of behavior that you cannot achieve in traditional TCP/IP because you don't have this kind of programmability. You know, there are things that you are stuck with, and you cannot do anything with unless you will completely change certain protocol or completely change certain specification. Sorry.
Yeah, and that's basically the end. Here's just some mention of our framework. So the lowest are just deliverables.
We have 6 references, 3 of them ours, okay, that doesn't count, but 3 of them from other, let's say, institutions that use it, and we just hope that it will use it more.
And yeah, and here are the links where you could find our simulator. There's code on open source project. There are some major releases, basically every month. Snapshot is over here, and the step by step you can find on GitHub. There's commits like I would say every day, but at least every week. And for some live presentation, move over here. So here is very simple scenario where you have just 2 hosts, no routers. And the host has only one IPC. As you can see, there is a cross, meaning this IPC is not enrolled in the diff, in the layer. And when we start running it, the application process issues request for reflow. It gets resolved to best address. Just how can we receive it? How can we reach it?
Kind of analogical to the DNS. You know, if you have application just like a ping or web transfer, first it needs to resolve the name and create a communication channel for passing the data. So it's right now happening.
And
so there is a flow allocation.
Stop it. You can see the structure is as I posted on the as I showed you before, but here there's nothing. No, there is just something we call mock EFCPI. There is just for some management connection, but it does not provide the reliability, flow control, and other stuff. And if we just run it, once the request arrives, a new module will be created.
One level.
So yeah, most of the modules are created on fly as the application request connection, all the necessary modules, all the data paths are created, and if we go level up, we can go inside the relay and multiplexing task, and there is something called port. We have input queue, output queue, and there should be there's the actual port that is connected to the layer below.
We really like about OMNeT, the ability to create simulation modules on the fly, because this is what we are using a lot, you know, because if we are speaking about recursive architecture, a lot of things are not present in the layer. It needs to be created on some recursive calls. So thanks to this, thanks to the hooks that are already present in OMNeT, we are able to mimic what is basically happening in the real operating system. You know, if there is some communication, we need to create some shared state. That means that you will need to create some modules that will hold the state. This kind of stuff.
So if you want to change behavior of your transport protocol, you can implement one of those policies and change the behavior. You just want to send acknowledgement in a different way. You want to generate initial sequence number in a different way. You want to change receiver control acknowledgement policy. You can just implement this policy.
This is what we also like about OMNeT, like the ability to create module interfaces that is already present in nets, because otherwise it will be problematic to change something on the fly.
Yeah, and there is also window control policy and flow control policy present. You can choose which one do you want to use, or you can use both, and then you have to implement policy that will handle situation when those policies saying different stuff, like one says send more and the other says no, so which one have preference and stuff like that. But you can choose to use just one or to not use any flow control at all.
Just to put, let's say, the difference between mechanisms and policies, like in the RINA, like imagine that you have some link layer correction, can use either CRC or you can use some different kind of the message code authentication and hashing. So like the mechanism is that you are protecting something with the message authentication code. The policy is what kind of code you will use. You know? Like there are certain things in computer communication that are fixed, just like fragmentation. But it's up to you how you will do the fragmentation. Whether you will automatically slice it to the smallest possible pieces, or whether you will try to use the bandwidth as efficient as possible.
Yeah, and I would like to use this opportunity to ask guys responsible for developing OMNeT if it's possible to somehow tell this module to connect to the bottom of the compound module that it is inside of, because I just put in some empty module that I call South Gate and North Gate just to get the connection to the bottom and to the upper end, so where I can see which way the PDUs actually flows.
Because otherwise it's choosing the shortest path towards the edge.
It is possible. Okay.
This place doing like M or something like
Okay.
which south, east, west.
Cool.
Great.
This is the thing that we've been looking into, like the OMNeT manual, like it's tooltips about the update string, this kind of stuff. If there is something definitely, I believe there are some parts missing here from the description, or not?
I don't think it's because it's
okay, we will definitely look for it.
But maybe the description isn't very clear.
Okay.
It's more like
Yeah, and I guess that's all. And thank you for your attention. Or if you have anything to ask, so go ahead.
I have a question. You have mentioned that there are a lot of components that you can turn on and off and things like that. I'm just wondering, how do you define the wire format? I mean, if
How do you
somebody
define what?
the wire format? I mean, the bits on the wire or on the medium. I mean, if somebody wants to implement or a new system that is interoperable with your system, does he have to implement all the possibilities? I mean, so because
let's say basically how you can adopt this technology in real life. You know?
yeah,
like
because in real life probably there would be
there will be just Ethernet or there will be
vendors and then it
yeah.
would be an interoperable problem.
Like there is a specification how you can run this RINA over Ethernet. You know, so like basically you will have Datalink header, and after this RINA will start. You know, so this is the way how manufacturers can create this kind of implementation using Ethernet. And right now we are not having any modules, simulation modules that are mimicking Ethernet behavior. You know, so for us it's like simulation of the link layer is only done based on parameters just like delay bandwidth. You don't have anything like interframe gaps and something that is happening on the real main layer.
Yeah, the Linux kernel implementation that is developed within the Pristine project actually uses the Ethernet header, and we didn't want to use anything except RINA in the simulator, so we have just everything RINA. But yeah, as Vladimir said, we can run it on top of Ethernet, on top of UDP, yeah, whatever.
So if there are two nodes, there are a lot of options that go in both every layer. So do they do some kind of negotiation with the options?
Yeah, it was something that Marcel showed initially, and it's like this green hook on this orange box, and this kind of something called enrollment, when communicating parties are negotiating what set of policies are using. Because if they will be using different
support. Different vendors.
mutually exclusive policies, that will be a problem. But there are parts where they can use different policies and still be able to communicate. But this is definitely an important part of the operation of this architecture. So that would be it. Like, I know we have only 3 references. We hope that more will be coming in next years when these things will be getting more and more, let's say, popularity, because there are already other upcoming EU projects that not even us are involved in, but they stated that they will be using basically the RINASim as the baseline for certain features development. So we will be definitely interested if there is any option how to mark RINASim as one of the, I don't know, official OMNeT it's up to you. I don't want a decision right now, but if you will keep it in your head and maybe next year when you will see more work on this, that would be great.
We are happy to add the protocol website and logo to the OMNeT front page.
That would be cool. That would be cool. Okay.
Is there any chance of using it in production somewhere?
Like I would say, technology readiness level right now is marked, I would say, 6. So there are 3 independent implementation of this, but I don't think they are ready for enterprise deployment. You know, like still I would say the kind of academic toy to play with. But in 2 more years, and Marcel will be working on it, on the real implementation and others, I believe it will be definitely not a replacement of TCP/IP because it's the same situation like with the Joseph. You know, you cannot convince somebody to invest a lot of money into just an idea. It must be better, visibly and clearly better than some things. But we believe that this architecture may be good for certain use cases, like the use cases for the banking sector, because these IPCs, these orange boxes, are kind of black boxes. You don't know what is happening inside unless you are at the same rank. So if you are 1 layer up or 1 layer down, you don't know what is happening. Also, there is kind of the isolation of the communication. It's good for the encryption, you know, because you don't see any management traffic, or it's hard to decode what is happening in the network without not being on the proper level of this recursive architecture. So I believe on certain use cases of computer networks, this architecture may have really good impact.
What you just described could be a killer scenario for this RINA technology architecture. What I'm saying is that that kind of scenarios can be done only with RINA or maybe also done in current internet architecture.
Of course, there are scenarios that can be done with existing architecture. Just like that, take for instance the multicast. You know, like multicast, good idea. It is being used only for the streaming because you cannot go forward or backward with the multicast streaming. Hence, when you are watching YouTube video, still it is a unicast. You know, and when 1,000 people are watching the video, still it's one unicast stream. You know, so because it is really hard also to make acknowledged multicast stream that somebody really received it. You can achieve this quite easily with the RINA. And other different use cases can be solved easily with the RINA.
Marek, if I may, one use case, and it's a part of Preston project, is data centers. Because in data centers, you are just communicating very locally, but you are using application layers protocols, or at least transport layers protocols to do the communication between those which are just physically one by side. So maybe it's too much overhead in TCP/IP networking in this case because you are creating all the layers and you need to go through the TCP/IP system. In this case, you would have only just the 1 layer or maybe 2 layers for the communication. So I guess it's not about replacing or solving things that cannot be done right now, but maybe sometimes to bring the benefit of making it easier than the existing solution. That's the, I think, the idea behind it.
But my impression is that the networking area is one of the most conservative because it's involved with multiple parties and we need definitely a certain common promise which is called protocol. So this is not different from just computing protocol, just a single device. You have a very innovative idea, you can just make it. Right? And this replay, whatever. But communication is always involved with multiple parties. And TCP/IP, this is just my personal comment. This started in the 1970s and then stand up weathering all kind of challenges. And you remember that my PhD thesis topic was on ATM, DISDM. This is right now gone. Right? Hope you some maybe old enough can remember that 1990s or 1980s, even at the universities, they never thought about the TCP/IP because they believed that TCP/IP is the legacy protocol, so this will disappear very soon. So when I was a student, I had no chance to learn about the TCP/IP because all the professors believed that TCP/IP, even Ethernet, will disappear very soon. But right now we see that actually the other way around. So ATM DSN is gone because of its complexity.
the promises many things, but so come then suddenly happens, the internet catch up with all those quality of service, blah, 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 blah. And right now we are living in the world of the internet. This is also very good, but I'm just a little bit big question mark. Maybe this is another version of the website.
We shall see. Like, if I can suggest you one book that is worth of reading on this topic, about different networking architecture, about things that been there 20 years ago and right now are being once again discovered with the different name, the same idea but with the better PR, so we discuss it. Read this book, Patterns in Network Architecture, by John Day. It's kind of the guy who worked on the ARPANET since the beginning, and he was one of the grounding chairmen of the ISO standardization, and he has a lot of stories about how all the standardization efforts went really bad and end up in a thing of creating something worse, you know, like when there was a chance to make a bad decision, this decision was taken, you know? And at this book are outlined also the basics of this RINA architecture. So I'm not propagating it for RINA, I'm propagating it for the historical value of this book, because this guy has 30, 40 years of networking experience, and it's great to read all the things that he's mentioning over there. Like right now everyone is gossiping about moving towards IP version 6, and if you take into account like moving from the ATM to the TCP IP, before that moving from the modem connection, like moving from the MCP protocol to the TCP, like computer networking, what is staying there for such a long time? Every 10 or 15 years there's some major design or redesign of the computer networking that a lot of people have to adopt. Right now, it doesn't happen, it didn't happen for 20 years after IP version 4 was adopted, but still, we are working with the protocol. The specification is from 1983, you know? And there are a lot of bugs hidden in TCP IP that were not apparent during this, in the year 1983, because at the time, there was no World Wide Web. At the time, there was only Telnet, FTP, and Mail, and that was all free applications. And since that time, we developed a lot of how we are using internet now, how it influences our world. Yeah.
And that is not pirate, that is Professor Day.
Yeah, that's Professor.
Is it a real photo?
Yeah, it's real photo.
Oh.
Yeah,
That's
really
really
light on one eye.
Yeah.
So yeah, so this will be for the dissemination. Yeah.
Oh, one final comment about this book. Actually, I didn't read that, but I just checked this into Wikipedia, and looks like the key idea is that you just try to rebuild the whole network based on the IPC idea, right?
Yes.
Interprocess communication. But again, I remind you, back in 1990s, the last of the computer scientists actually they believe that OSI or satellite or whatever is already done. So they just try to build another new step on top of OSI based on exactly the same idea. So they believe that OSI satellite whatever is completely done. So they just concentrate as one black box. Okay. So assuming that okay, there's a connection or link is between and those is already done. So we don't care about any more. On top of that, they just try to build another particular step or much like IPC or district commuting. That was back in 1980s or 1990s. So what I'm trying to say, again, this is definitely innovative, but again, it looks like revisiting.
Like he's using the ideas that he thought is worth it to pursue. You know, like the ideas that were there. You know, like this EFCP protocol that Marcel mentioned for the data transfer, they say between TCP and TCP. It is based on work from one guy from Liverpool Laboratories in 1983. So, and the idea is great, you know, but it was never adopted. Instead, TCP won. And so it is even about reusing somebody else's work to make something generic, you know, something that is able to, let's say, satisfy any computer networking use case, just like the acknowledged multicast, you know, or just like the outgoing traffic engineering that you can really configure you as an administrator. This kind of stuff. So it's not. I would not say that the RINA is only about the ideas of this guy. He was the one guy who assembled the pieces from others. We thought that it is worth it to have in generic architecture.
he also mentions it that it's not his. It's RINA is not his. He just put together the ideas that were there. Just people didn't see them. No, it's not.
One point I can make, because based on my personal experience in networking, the chances are the importance of this RINA project or RINA approach is rather than maybe creating something completely new, network architecture replacing the existing one, but from this activity we learn a lot and then return that idea back into TCP. Like it was like ATM, PSN, MPLS, lots of ideas, but right now it's reflected back inside the TCP Internet Network. In this regard, I think.
Even that would be a great outcome. You know, if you don't be never deploy, but you will learn once again something about computer networking and some mistakes that we've done in TCP/IP and that we are able to amend. But just taking into account how long, let's say, was the standardization process of HTTP, you know, and suddenly the bodies, just like IEEE or IETF, are not able to find consensus really quickly in a way that it will make an impact. You know, companies are way ahead of them because companies need to make business and they are able to come with a solution faster, even though it is not a standardized solution. You know? So it's always hard to speak about the consensus and IETF, I would say.
Okay, I think it's really interesting topic, but we are like 20 minutes at a time, so thanks a lot for your presentation, and we probably should go to the next big thanks to you. We go to the next session about INET. We have Rudolf and Levente. We'll be presenting the current status and new developments of INET and